So today we're going to start looking at some cycle questions. We already looked at the Otto cycle, but now we're going to start looking at them a bit more generally. So we'll look at a Rankine question, we'll look at a Brayton question, and another Otto question. And hopefully by the end of those, they're pretty clear, at least how to do them in general. So we'll start with the Rankine one. 6.2. Steam is the working fluid in an ideal Rankine cycle. Saturated vapor enters the turbine at 8 megapascal, and the flow leaves the turbine as a saturated two-phase mixture with a vapor quality of 67.45%. Saturated liquid exits the condenser at a pressure of 0.075 megapascals. The net power of the output of the cycle is 100 megawatts, and the pump consumes a specific work of 8.06 kilojoules per kilogram. Calculate for the thermal efficiency of the cycle, the mass flow rate of the steam, and the rate of heat transfer in the boiler, and the rate of heat transfer in the condenser, and calculate also the mass flow rate of the cooling water. So this would be in the condenser, if the water enters the condenser at 15 and exits at 35 degrees Celsius. Okay, that's a pretty long question, so buckle up and let's get started. So yes, this is a cycle question. So let's just briefly review the Rankine cycle. We have 4 steps. So we start at state 1, all right? We start at state 1 and we go through a pump. So what does a pump do? It just adds pressure. It brings your pressure up. So by the time we get to state 2 over here, we're at a higher pressure. Then what happens? Well, we go into a boiler, and the boiler increases our temperature, but does so isobarically. So the pressure from 2 to state 3 stays the same, but the temperature goes up. Okay, what next? Well, then comes the fun part, is we have the turbine. So the turbine, we are a superheated vapor at state 3, and we expand through the turbine all the way to state 4. So we expand through, we're going to be at a lower pressure and a lower temperature. So if it's not isothermal and it's not isobaric, what type of process happens in the turbine? Well, it's an isentropic process. So if we know the entropy at state 3, we also know the entropy at state, at state 4. And of course, this is a cycle, so we have to have that sort of closure where we go from state 4 to 1, and we do this in a condenser. And it's in the condenser that we have our Q out, which is the wasted heat. We also have our Q into the boiler. And it's the turbine that's giving us the work output that we want. Now, of course, it costs energy to run a pump in any Rankine cycle, and we're told, thankfully, how much energy that costs us, right? We're told it costs us 8.06 kilojoules per kilogram to operate this pump. So if the net work output is 100 megawatts, the total work that we need to be able to produce in the turbine is a bit more than that, because we need to sort of redirect some of that to the pump so that we can keep the cycle going. Like so. Now, keep in mind, in most Rankine cycles, you can oftentimes neglect the work of the pump because the work of the pump is pretty small in comparison to the work in the turbine. But since they give us an actual specific value, we're going to go ahead and assume that it's important. And if later on we see that it was small, then it was small, and we can, neglect it later on, or say that it's negligible. All right, so back to the actual question itself and the numbers they give us here. Okay, so steam, the first thing they tell us is that the steam enters the turbine. So that's state 3 is where we're entering the turbine as a saturated vapor at 8 megapascals. So sat vapor 8 megapascals. All right. So let's go to the property tables, and let's look at what happens at 8 megapascals of pressure at the upper limit of things. Here's 8 megapascals of pressure. Okay, so we have Hg, that's our enthalpy. We have our entropy, which is important because remember, like we said, the entropy at 3 is the entropy at 4. So we're definitely going to want to know that. So these are the two values that are going to be most important. So in this case for state 3. So 2758 and 5.7, well, let's do it one at a time. 2758 and 5.7432. So at state 3, we have H equals 2758 kilojoules per kilogram. And, oh yes, and entropy is equal to 5.7432, and the units are kilojoules per kilogram Kelvin. I just forgot it, 1 second. 5.7432. 5.7432 kilojoules kilogram Kelvin. Okay, so this is the important stuff going on at state 3. And then we're told, the next piece of information we're told is saturated vapor enters, it leaves the turbine with a vapor quality of 64.7. So if we look at state 4, and we know that x equals 0.6475, that's good. That's, one thing we know is it's at 7.45. But we know that the entropy has to equal as well. S equals 5.7432 kilojoules per kilogram Kelvin. And that's because the process from 3 to 4 is, I'll try to write this as clear as I can, isentropic. So S3 is S4. So now what we're going to try to do is find a mixture from the mixture tables, which has exactly this value of enthalpy at 64.75. So how are we going to go and do that? Well, it would be pretty difficult to just start going and looking through, because we would have to go to every single line and start checking what the entropy is at 64.75 quality until we get something. We obviously don't have the time, or we just can't do that. Maybe there's some other bit of information we can use that can help narrow our search down. Well, remember that we said any heat addition or heat rejection process is isobaric. And that means going from 2 to 3 is isobaric, and going from 4 to 1 is isobaric. Now, if 4 to 1 is isobaric, that means we know the pressure at both states, or if we know the pressure at 1, we know the pressure at 4. And if we know the pressure and the quality at 4, then it's much easier to find out what the enthalpy is, right? So if we go back to the actual question, let me reopen it. If we go back to the actual question, it says the saturated liquid exits the condenser at a pressure of 0.0075 megapascals. So if the pressure we're exiting the condenser, state 1 is 0.0075, well, because I know state 4 to 1 is isobaric, then it means state 4 is also going to be 0.0075 megapascals. So if I look for a mixture at 0.0075 and 64.75% quality, well, then I don't even really need the entropy in that case. I can find the enthalpy by doing what we've done a million times before, right? Which is HF plus XHFG. So let's go see what that looks like. So 0.0075 megapascals. Where are we here? 0.0005. Here, 7.5 kilopascals. Good. So 7.5 kilopascals. This line is what we're interested in. If we look, we can just do sort of a check for ourselves on the entropy. So if we do 0.5764 plus 0.6475, 6745, which is the quality, times the change, I'm getting 5.753 as the entropy. Does that match up? Very closely. So we have 5.7432 there, 5.753, we're within some reasonable value. So just a sort of cross check to see that we're at the right place. Anyways, what we're really interested in here is the enthalpy, right? Because it's the enthalpy that's going to tell us about the work and the heat transfer. So a fluid of 64.75 quality will have HF, which is 168.79, plus that quality, so 0.6745, multiplied by HFG, which is 2406. And that's 1791.64. So H4, and this is really what we're after, is enthalpy in most cases, 1791.64 kilojoules per kilogram. Okay, so we found the enthalpy at state 3, we found the enthalpy at state 4. What do we know about state 1? Well, if we read the question very carefully, it says saturated liquid exits the condenser at this pressure. So we actually fully know the state at state 1. Oops. There we go. At state 1, we're just a saturated liquid at that pressure of 0.0075. So the enthalpy at state 1 is just HF, which we saw was 168.79. So H equals 168.79 kilojoules per kilogram. Outstanding. Now, what do we know about state 2? So we're told, what does the pump do energy-wise? It's just going to give us 8.06 kilojoules per kilogram of energy. So then that means that the enthalpy, I don't know why it keeps doing that, switching to the eraser. The enthalpy at state 2 is just the enthalpy at state 1 plus that 8.06. So 168.79 plus 8.06 gives us 176.85 kilojoules per kilogram. Now we're in a really good position. Why? Because we know the enthalpy at every single state. And if we know in a steady flow, for a cycle with a bunch of steady flow systems, if we know the enthalpy before and after, then we know the heat transfer or the work transfer between each of those states. So let's now maybe we can actually start answering specifically what they ask of us. So calculate for the thermal efficiency of the cycle. Okay, so let's start with that. We know thermal efficiency is going to be the work net over the Q in. All right, we're told that the net work is 100 megawatts, so that's awful convenient. What's the Q in? Well, like we said, now that we know the enthalpy everywhere, the Q in we can find by looking at the change in enthalpy where we add heat. So from 3 to 2. So H3 minus H2. So if we look at H3 minus H2, of course, times the mass flow rate. Wait a second. We don't know the mass flow rate, so we have to find that first, right? So maybe before we start looking at the thermal efficiency, we'll want to look at the what the mass flow rate is, which actually happens to be another question later on. So okay, let's go and find the mass flow rate before we do this, actually. Change my mind there. So how are we going to find the mass flow rate? Well, we're told that the net power output is 100 megawatts. So 100 times 10 to the 6 watts. And we know that the mass flow rate times the, times the change in enthalpy gives us the total power output, right? Now but what is the net work really? The net work is the work we get out of the turbine minus the work that goes to the pump. Sorry, I should be more specific here. So 100 times 10 to the 6 is going to be the work we get out of the turbine, which is, m dot times H3 minus H4. That's the work we get out of the turbine. Minus the work that goes to the pump, which is H2 minus H1. So we know H3, we know H4, we know H2, we know H1. So this was actually given anyways in the problem statement as 8.06, right? It's the work required to drive the pump, kilojoules per kilogram. H3, H4 we already found. And we're told, of course, that the difference between the drop H3 to H4 and the amount of work going to the pump is 100 megawatts. And that's the amount of work you actually get to use for whatever you want to do with it. So if we do 100 times 10 to the 6 divided by H3 minus H4 minus 8.06. So H3 minus H4 is 2758 times 10 to the 3 minus H4, which is 1791.64 times 10 to the 3. And all of that minus our 8.06 times 10 to the 3, which is going to the pump. If we do this, I'm getting a mass flow rate of m dot equals 104.35 kilograms per second. So this is the amount of mass flowing through the system in order to generate that much power. Now, you can kind of see there's a bit of scalability here. So for the same power plant, if you then decided to just pump more a higher mass flow, you would get a bigger power output, right? So the important thing just to remember is that the power output in terms of watts is basically just the mass flow rate times the change in enthalpy, or the net change in enthalpy that gets contributed to the useful work. So in this case, that's, as we saw, H3 minus H4 minus H2 minus H1, right? So that's the relationship between power and enthalpy, is that the power is just mass flow rate times the change in enthalpy that you get across a certain turbine. So what else do they ask us to do? Let's see. Find the mass flow rate. Oh yes, the thermal efficiency. That's why we found the mass flow rate. Okay, so the thermal efficiency, we saw eta T equals our work net, which is 100 megawatts, divided by Q in. Now our Q in, well, it's going to be also in terms of power. And specifically, what is it? Well, we know the change in enthalpy across the boiler where our Q in happens. And now we know the mass flow rate. So m dot times H3 minus H2 should represent that Q in that we're adding in the boiler. So if we do 100 times 10 to the 6 over m dot, which is, we found 104.35, times H3 minus H2, which is 2758 minus, typo, 2758 minus 176.85. And I'm getting 371 because that doesn't make sense. I forgot the orders of magnitude there. Excuse me. Okay, there we go, 0.3712. So we're getting about 37%, or 3712 efficiency. So a 37% thermal efficiency. That means of the amount of heat that we give to the system, 37% of that is actually being output as work that we can use, right? And of course, this considers the amount of work that goes direct to the pump. We don't get to use that. It doesn't contribute to our net work. So make sure when you're doing thermal efficiency, you're not just considering the H3 minus H4, you're also remembering to subtract whatever work gets put into the pump or the compressor. And for a Brayton cycle, this is usually a significant amount of energy. Okay, so moving on, we have now found thermal efficiency, mass flow rate, rate of heat transfer in the boiler. Well, we used that just now to find thermal efficiency. We can calculate it separately. It's just the denominator here. So 104.35 times 2758 minus H2, which is 17685. And it's in terms of kilowatts, but they want megawatts. So let's just divide it by 1,000. 269.34 megawatts. So Q in equals 269.34 megawatts. Okay, and let's say we wanted to do it another way, because now that we know the thermal efficiency and the network output, we could have just divided the network output by the thermal efficiency, and we would have gotten the same thing. And that's just by rearranging this guy here. Anyways, I should be boxing my answers here. M dot Q in thermal efficiency. And then the rate of heat transfer in the condenser. So exactly the same thing, but we're just using the enthalpy drop from 4 to 1. So if we do M dot H4 minus H1, which is 104.35 times H4, 1791.64 minus H1, which is 168.79. So this is how much enthalpy we're losing, and turning that into megawatts, it's 169.34. So we're losing 169. Sorry, I should be writing this down. Sorry. Oh, I did over here. Sorry. 169.34 megawatts. Okay, so we're rejecting 169.34 megawatts. Now, another thing we could have done to calculate this instead of calculating it with the enthalpy drop is that since we know Q in and we know the total work output, we can just do the Q in minus the work output, and that will have to necessarily equal the Q out of the system. So you can do it that way if you already know these two, which we did, or more generally, assuming you know all the enthalpies at all the states, which is generally a good first step, you can just do it this way. And that's the amount of heat transfer in the condenser. So calculate also the mass flow rate of the cooling water in kilograms per hour. Oh, excuse me, actually they want both mass flow rates in kilograms per hour. So we just have to multiply both values by 3,600. But I'll do that after. For now, I want to keep focused here. So if we have cooling water, right, we're rejecting heat to something and we're rejecting it to the cooling water. So we're told that the cooling water, I want to see what I can erase here. I'm going to erase just the picture of the cycle. I don't think we need it anymore. Okay, so if we want to figure out how much heat we know how much heat we're ejecting into the cooling water. The question is, how much water do we need to pump in to be able to absorb that heat while raising the temperature of that water from 15 to 35 degrees Celsius. So I know the heat transfer to the water is the heat transfer in the condenser. So Q equals 169.34, which is what we just found. And Q equals MC delta T, right? Or in this case, M dot. C for water is 4.18-ish. And delta T is 20 Kelvin or 20 degrees Celsius. So 20 because we're going from 15 to 35 degrees. And if we solve for the m dot in this will give us, by the way, kilograms per second. So we have to remember to convert that into per hour. So divide by 4.18 kilojoules, sorry, so 4180 this should be, times 20. And I'm getting 25.59 kilograms per second, which let me just check if that's the right answer. Yeah, that's the answer. So it's a humongous amount of water. And of course, that's per second. They want per hour. So if we multiply by 3,600, we're getting something on the order of 7.29 million. Okay. And that's how we do a Rankine cycle question.